Today we will look at Book 4B, Chapter 12, more about basic properties of circles. So last time we looked at the opposite angles of a cyclic quadrilateral. So this time we'll look at the exterior angles of a cyclic quadrilateral. So first of all, a quadrilateral, if four of the vertex of it is lying on the circle, we call it a cyclic quadrilateral. And look at this figure here. So we got this quadrilateral PQRS, and the side PQ is extended to produce a point K outside the circle. And in this case here, the angle X is called the exterior angle of the cyclic quadrilateral. And angle Y is the interior opposite angle corresponding to X. So it is still about the opposite angle, but now one of them is interior and the other one is exterior. And for this interior opposite angles, if we look at this diagram this time, so RQ is extended to produce the point L, and then you can see this purple angle here is also the exterior angle of PQRS, and is also the interior opposite angles of Y. So therefore, in this case here, we can see that this interior opposite angle can actually have two exterior angles corresponding to it. And this is the second theorem we're going to talk about. So in a cyclic quadrilateral, the exterior angle is always equal to its interior opposite angle. So in this case here, X is equals to Y, and when you write the reason, please write exterior angle cyclic quadrilateral. And let's look at how we got this theorem. So let's look at the proof together. So in this figure here, PQRS is a cyclic quadrilateral. PQ is produced to K, so therefore you got an exterior angle X here. And if we look carefully, this one's, okay, if we name this angle Z here, Y and Z add up together is actually equals 180 because of your opposite angle cyclic quadrilateral. And this X and Z add up to 180 as well because of adjacent angles on straight line. So therefore, if we substitute, we put both of the equation together, you realize X is equals to Y. So this is how we prove this here. So after looking at the proof, again, let's look at how we can use it to find some unknown. So in this figure here, triangle ABE is an equilateral triangle, meaning that all the lengths are the same, all the angles are the same. And then ABC and CDE are straight lines. And it says if BED is 25 degrees, find theta and the other unknown. So find these two angles here. So first of all, you can see that this two angle is almost outside the circle, and there is no information near it. So let's look at the information we're given first. So it's an equilateral triangle, and what do we know about it? All the lengths are equals, all the angles are equals, and then we exactly know the angles as well. So angle BAE and angle ABD and angle AEB are all 60 degrees. Okay, so all of them are 60 degrees, so let's write down. And this is because of the property of equilateral triangle. Okay, but then let's look at what we want to find first. So let's look at theta. Theta is here. So I use another highlighter to let you have a look. So let's look at this yellow one here. So this is a cyclic quadrilateral because all the vertex are on a circle. And therefore, we can see that this theta here is actually the exterior angle of the cyclic quadrilateral. So therefore, theta is equals to angle BAE. Exterior angle cyclic quadrilateral. Okay, remember it is equals to its interior angle of the interior opposite angle. So therefore, in this case, it's BAE, which means that theta is 60 degrees, right? And once we got that, let's look at the other angle there. So the other angle is also the exterior angle of a cyclic quadrilateral, but this time is opposite. Interior angle is AED. So let's write down first. And let's look at AED here. So AED is this angle. So therefore, is actually your AEB plus your angle BED. And AEB is 60 degrees because of an equilateral triangle, and then this one is 25. So therefore, adding up together gives you 85 degrees. So let's look at another examples together. In the figure, ADE is a straight line. So if angle EDC is 63 degrees and the arc length AD is to arc length DC to arc length CB is 3 to 4 to 5, find the angle BDC. So first of all, let's look at where is BDC. So this is your BDC here. Okay, and look at this here. This angle here, if we look carefully, you can see that this is the exterior angle of the cyclic quadrilateral. And what do we know about the exterior angle of a cyclic quadrilateral? We know that it is equals to the interior opposite angle. So therefore, we have to find which one is the interior opposite angle. So in this case, you can see that angle ABC is the interior opposite angle of angle EDC. So they equals each other. Okay, so write the reason. And then let's look at the next information. The next information is the arc length proportions. Okay, so therefore, you can imagine you probably use your arc proportion to angles at the circumference. But let's look at the information here first. So what kind of arc is this? CB. So this is your arc CB, and if we're talking about the angles at the circumference, it is actually the angle you're looking for, angle BDC. And then let's look at the other arc as well. So arc DC is this one, okay, and then the angle is DBC. Okay, so let's use the pen here. So this is the angles at the circumference, and then the last arc, AD is here, and the angle is this one. Okay, so in this case here, you realize you have the angle ABD and the angle of DBC, okay, according to those arc length proportions you have. But the thing is, you don't know what are those angles. But you know that they add up together will give you angle ABC, which you just found is 63 degrees. So therefore, let's write out. We do not know the angle, but we do know what is the ratio of it. So it's equals to the arc AD to the arc DC, which is your 3 to 4. And the reason of that is your arcs proportion to angles at circumference. Okay, and then after we got this 3 to 4, then we can use the ratio to find the answer. Okay, so therefore we will use the ratio to find what is the angle DBC here. But first of all, why we want to find DBC? Because angle DBC to angle BDC, we know that is equals to the ratio of arc length DC to arc length CB. So in here again, we use the arc proportion to angles at circumference. Okay, so we know that the arc length DC to CB is 4 to 5. And angle BDC is the one you want to find, but what is the angle DBC? So angle DBC here, okay, so this one here is just part of the angles of ABC. So we know that it will be your angle ABC, which is 63 degrees, the total angle, times the ratio. So this part of the ratio is 4, this is 3. So 4 and then over the total ratio 3 and 4 together, then you have 63 times 4 over 7, which is 36 degrees. So therefore, this is 36 degrees. And ratio, you can write it as fraction. And now you can solve it. So therefore, your angle BDC will be 45 degrees. Okay. So after this, I would like to look at a few more questions in your Consolidation Exercise 12A work. So Consolidation Exercise 12A, let's look at question 4. So question 4 here, we have to find the unknown. So highlight the unknown. And you can see angle X is outside the circle, outside the cyclic quadrilaterals, and it is the exterior angle of the cyclic quadrilateral, and angle BDE 88 degree is also the exterior angle of cyclic quadrilateral, and you know that it is equals to the interior opposite angle. So therefore, in this case here, these two are equals each other. So this one is just an easy question, so let's do it quickly. So angle DBF is equals to angle ACD. So remember to write your reason. So therefore, X is equals to 76 degrees. So make sure you write X is equals, don't write just DBF. Angle DBF is equals, because the question is asking for the unknown, and angle DBF is not the name of the unknown. And using the same reason again, your Y is gonna equals to that 88 degree. So again, make sure you write Y equals 88 degree. Okay, so very quick. And then let's look at question 6 here. Question 6. So look at the unknown you want to find. So it's outside here. But is that the, look carefully, some of you might think, oh, that's the exterior angle of cyclic quadrilateral. But is that true? So be careful, your exterior angle of cyclic quadrilateral is this one here, not the R, because it's always the original line. Let's do this. The original line of the cyclic quadrilateral is CD, and this line extend. Okay, you extend with this line, and the other line extend. So therefore, angle CDE is the exterior angle. So angle CDE is the exterior angle. Then look at it. Which one should you be looking at? The interior opposite angle will therefore be this angle ABC. But the thing is, you do not have ABC. So what other information you have? You got this parallel line here. So what does a parallel line tells you? So you can see they create this C shape here. So therefore, you can use your interior angles parallel line. So those two angles adding up together will give you 180. So let's write down. So always have an overview of how you're going to write the stuff before you write it. So think backward. So you're using the parallel line, so therefore write parallel line there. Do not write supplementary. So angle ABC is 93 degrees. And once you got ABC, then we can use our exterior angle to find angle CDE. So this one, exterior angle cyclic quadrilateral. Okay, and then after this, we're not looking for this red angle here. We're looking on the one on the side, the angle R, and this is a straight line, right? So therefore, because FDC is a straight line, so therefore EDF adding angle CDE is equals to 180. The reason is your adjacent angles on straight line. So R plus 93 gives you 180, so R is equals to 87 degrees. So question 11. The unknown is here, and you can clearly see that this is your exterior angle of the cyclic quadrilateral. If you still can't see it, just highlight it a little bit so that you can see it. Okay, and then you have to find this unknown. But the thing is, the angle you have is, the exterior angle supposed to equals to the interior opposite angle, which is your ABC. But the thing is, you don't have this ABC here. So how do you find the angle ABC? So you got part of it already. You got this angle ABD, but the thing is, what is your angle DBC? So that you can add them together to create your angle ABC. So we do not know what is our angle DBC, but we have this angle ADC here. So let's look at this. How is it going to help you to find it? So remember this shape here. So therefore, we know that our angle CBD is equal to our angle CAD. And the reason is your angles in the same segment. So again, things from your chapter 11. So therefore, it's equals to 27, and your angle CDE is equals to angle ABC, as we mentioned, is your exterior angle and cyclic quadrilateral. So therefore, is equals to angle ABD, adding your angle CBD. And on this side is angle C here. So 53 plus 27 degrees gives you 80 degrees. And let's look at question 12 as well. So question 12, the unknown is here, Z. Okay, so we don't know what is angle Z, but here, this 110, look carefully, is not your exterior cyclic quadrilateral. It's not your exterior angle cyclic quadrilaterals, because it combines a little bit of the inside part. Angle DCB is the interior, okay, part of the interior of the cyclic quadrilaterals, interior angle of the cyclic quadrilateral. Okay, so therefore we have to look carefully. What other information we have? We got a parallel line again. Got a parallel line and we got a set shape. So therefore, we somehow know that we can use this alternate angles parallel line to find that this little one here is 37 degrees. So if angle DBC is 37 degrees, then we know that this outside part here is another color. This outside part here is actually 110 minus your 37 degrees. So now you have your exterior angle. And once you have your exterior angle, you realize this is actually your interior opposite angle. So we have an overview now, then we can start writing. So first of all, write that red one, the red angle there. So because of your alternate angles, parallel lines. So make sure you're familiar with the shapes of those parallel lines. You're looking for the set shape, the C, or maybe the F shape. Okay, and then angle CBE, adding angle CBD is equals to angle DBE. So adding 37 equals 110, and angle CBE is therefore 73 degrees. And CBE is the exterior angle, so it adds up, it equals your interior opposite angle. And your interior opposite angles is made up of your ADB and CDB, which is your 37 and Z. And CBE on this side is 73, so therefore Z is 36 degrees. Then we look at question 17. Okay, in here, they provide some information. So AD equals DC equals CB, and then angle CBE is 120, and they ask for angle ACD. So this is the angle ACD. And somehow you know that this DAC is the same angle because of base angles isosceles triangle, as they provide these two lengths are the same. So let's look at what other information we have. So we got this, and this angle here is your exterior angle of your cyclic quadrilateral, and it will equals, this one here will equals to the opposite interior opposite angle, which is CBE. ADC, which is this one. So if you got this orange one here, then obviously you can find the red one on the side. So let's write it down now. So angle ADC equals angle CBE, which is 120 degrees. Okay, and then in the triangle ACD, because AD is equals to CD, therefore angle CAD is equals to angle ACD. Base angles isosceles triangle. Okay, and angle CAD adding angle ACD adding angle ADC is equals to 180 because they are all in this triangle. So angle sum of triangle, and because ACD is the same as CAD, so we can replace it, and then this is 120. So 2 of the angle ACD will equal 60 degrees. So angle ACD is 30. So when you write your base angles isosceles, make sure you write that those lines are equal first before you can write it, and make sure your reason is this one. So let's look at part B. So part B says, is AB a diameter of a circle? How do we know whether AB is the diameter of a circle? So we will be using our converse of angle in the semicircle. If we can prove that your angle ACB So right on the side, I want to prove that ACB is 90 degrees. If I can prove this, then I can prove this. So how do we find ACB? Is another color maybe? So this one here, how can we prove it is 90 degrees? So there's a information we haven't used so far. So this length here, we haven't used, right? So these are the chords, and when you have equal chords, you know that you have equal angles. Why do we want to know the angles? Because in here, we do not have any information inside this triangle. And actually, we can try to use it. So let's see how we start. So because we got this equals chord, then we have this angles will be equal. Because of equal chords, equal angles. Right? So this is 30 degrees. So if you can't see it, let's erase this part so we can draw it on there. You can see it clearly. So BC and AD. So here is your BC, here is your AD, isn't it? Okay, so this is the chord of BC, and therefore the angle corresponding to this is your angle BAC. And then you have this chord AD here. So the chord AD, the corresponding angles will be your ACD. So these two will equals. And this one here we just found is 30 from part A, isn't it? So therefore, you know that angle BAC is 30 as well. So once we got this angle here, what is the use of it? So write down, you got 30 here, and you want to know whether this is 90, isn't it? And look at here. You got this angle. This is also an exterior angle of the triangle ABC. So let's write down. So I probably write here. Okay. So in triangle ABC, your angle BAC adding angle ACB will equal to angle CBE because of exterior angle of triangle. So therefore, 30 adding ACB is equals to 120 and ACB is 90. And once we can prove that this is 90, we can say that AB is therefore a diameter of the circle. And make sure you write the reason. For proving, we need to write the reason. This is your converse of triangle in semicircle. So you have to be very familiar with all this. Let's look at question 21 together. So BD is a diameter, and then you have AD equals DE, and then angle ACD is 46. And then they ask you to find ADB. So ADB is here. Okay, so angle ADB, you can see that is inside the triangle ABD, but then you don't have other information in that triangle, so therefore we have to create some ourselves. So if they tell you that this is the diameter, what does it mean? You know somehow there is a 90 degree in there because of angle in semicircle. So angle, if this BD is a diameter, then this one has to be a 90 degree. Okay, so now you have one more information in that triangle ABD. So therefore, you probably want to find the other angle, angle ABD, in order to find ADB, because if you got two angles inside a triangle, you can find a third one. But how can we find ADB? ABD, sorry. So how can we find this one here? So look at the other information they provide. You got ACD is 46, and look at this. What kind of shape is this again? Okay, so you know that angles in the same segment. So this will be 46. So therefore, after that, you can use your angle sum triangle to find your angle ADB. So let's write down now. BAD is 90 degree, angle in semicircle. And then angle ABD is equals to angle ACD equals to 46 degree because angles in the same segment. And therefore, in the triangle ABD, BAD adding ABD adding angle ADB is equals to 180. Angle sum of triangle. So 90, 46, adding ADB. So angle ADB is equals to 44 degree. Okay, so that's you have been using your chapter 11 stuff here. You can see we haven't used chapter 12 stuff yet, but in part B, let's look at it. So they ask you to find angle EDF. So EDF, let's look at where's your EDF for part B. So this is a little bit messy, so let's rub it out. So EDF, this one here. And by looking at this, you might be able to see it already. So EDF is actually the exterior angle of your cyclic quadrilateral. And then you know that if we want to find that, we will have to find the interior opposite angle, which is this one here. Okay, so this one here, we do not know what is the answer, but we know part of it because just now we proved that this one is 90 degrees. So therefore, we have to find this angle here. So what is this angle here? DAE. How do we find it? So we got some more information we haven't used. This AD equals DE. You can see that this is this. So we have this isosceles. So this will equals this as well. And therefore, how can we find it? We got two angles and we want the third one. Okay, but obviously this third one is not gonna be your DAE because ADE because that part EDF, we do not know it, and that's what we want to find eventually, isn't it? So we have to find this angle DAE or angle DEA in order to find FDE. So therefore, don't try to think about your ADE. But the thing is, we always said if we got two angles, we can find a third one. So that two angle, now we have is this interior. And then we want to know what is part of this in here. And then look at this here. What is this angle? So this angle is actually your angle BDA. Okay, if you don't record it, it's actually your ADB. So this is your angle ADB here. So you got 44 degrees. So once you got your exterior, you know exterior is these two adding up together. So therefore, you can find what is your angle DAE. So let's write down first. So first of all, start with the information you got, the given length, and because of that, you know this is your isosceles triangle, and therefore the base angles will be the same. And once you got that, using your exterior, you can show me that DAE and DEA is equal to angle ADB. And because DAE is same as DA, so let's do just 2 DAE. So 2 DAE is actually equals to 44 degrees, which you found in part A. So the angle DAE is 22 degrees. Then we have this and this, right? And therefore we can find EDF, because EDF is equals to BAF, and BAF is actually just BAD, adding your DAE, because this is your interior opposite angle. So here you go, and then it is your 90 degree, adding 22 equals 112.